Okay, so last class we talked about Bayesian networks and how they could capture excuse me, how they could capture conditional independence relations between variables, which are usually more useful, in many scientific domains. Okay. And today what we're going to do is basically solve the question that we asked last time, which is, can we learn Bayesian networks that are trees? If we're not sure about general Bayesian networks, we have to place some constraint on the network. We saw that because arbitrary distributions can be viewed as Bayesian networks. And you cannot learn arbitrary distributions with a few samples. So we had to come up with some nice assumptions. And the one that we started out with, okay, the graph is a tree. And today, what we're going to do is do Chow-Liu algorithm. And then after that, we'll move on to undirected graphical models. Or these are also called Markov random fields. Okay. All right. And just as a reminder, our final assignment, assignment 4, will be posted today. And it is due a week from now, as usual, which is yes, May 31st at 10. Okay. Okay. So what's the Chow-Liu algorithm and where were we last time, right? Let's see. Okay. So let's do a quick recap. Really of the problem statement. We said the starting problem is input. We are given samples x1, x2 up to xn, over some alphabet sigma to the d. Each sample has d features and generated by an underlying Bayes-net distribution pt star. So there is some underlying tree t star that we don't know, but that's what's being used to generate the distribution, right? And our goal was to find a Bayes net pt again. This is like called proper learning, meaning you're trying to learn a distribution kind of from the same family, right? Again, I want a Bayes net, and the Bayes net graph is still a tree because we started out with a tree. It'll be nice to have a tree such that the distribution that we learn is close to the unknown distribution just from the samples, right? And how close is close? We want so that the KL divergence between the two things is at most epsilon. Okay, that's our main goal. And we relaxed it a little bit, right? We said, okay, if you want to do this, maybe let me make my task easier by saying, oops, what if we had even given a tree? Okay, I'm given a tree T2, but I don't know what the conditional distributions are. Okay, what's the best we can do? And here, maybe the tree is really bad, so you cannot get very close to the optimal, even if you use the best possible tree. But no matter, can I at least find PT that kind of gets close to the minimum? We're all T, we're all okay. Someone maybe gave us a tree, we want to find the best one. All right. So what does this mean? So pictorially, like we're getting, so let's say sample something like this. Okay, maybe this is the true tree. Okay, let me draw the true tree. It looks something like this. Okay, this is T star. We don't know. And the tree that we are given and we do know is maybe something like this. This is tree, this is T, and this is T star. Okay. We know T, we don't know T star, but we are given samples. And then we have samples like, X11, X12, X13, X1, and so on. Okay. So if I know the tree T, what should be the best conditional distributions to use? Any guesses? Like what should I put here? Right, so what are we trying to figure out? We are trying to figure out, okay, what is, so PT of a random variable. Let's say I say X equals X1, X2, X5 is going to be something like P of X5. I'm going to not put the equality every time. Hope it's fine. Condition on X5 and what else, right? Okay, so we are trying to figure out what these conditional distributions should be, right? Okay, given samples to minimize the distance. Any guesses on what you would put in there? You don't have, whatever, someone gave you a tree and told you, okay, this is a good tree to work with. What should the conditional distributions be? Yeah. Exactly, right? If you don't know much, then the only thing that you know are the samples, just look at the relative frequencies and work with them, right? So meaning the suggestion was, idea, use the samples to estimate P of xi given xj and use that. Right, I gave you a bunch of samples and I ask you, okay, what's the probability of x2, equals 0 given x1 equals 1? If you saw a sample like this, just use it. Just estimate the relative probability and you'll be done. Okay, does it make sense? How can I do such a thing? Well, given a bunch of samples, how can I estimate the conditional probabilities? Well, the conditional probability is really nothing more than the joint probability, right? Okay, so this is the formula for the conditional probability, right? How many times does I equal A, J equal B, divided by how many times do you actually see J equal B? Okay. So the algorithm would then be, to estimate this, over all samples, count how many times you have xi equals A and xj equals B. Okay, for each sample, over all the things, count how many times, maybe xi equals 0, xj equals 1, and all possible values in your domain. And sigma, is the alphabet, is a small alphabet, right? As I said, it's like ACGT or, 0, 1 or something small like that. Okay, so for every possible values, you just kind of estimate them, over all samples, count how many times you have xj equals. Okay. So if I use these things, I might end up with a so this way I can estimate p hat of xi. I'm putting a hat there just to denote that these are our estimates rather than the true values. Right? From our samples, we're doing some estimates, so you'll have some errors there. Yeah, but that's okay. And presumably, if I just ask you to estimate what's the chance that x1 equals 0, given enough samples, you'll get a pretty good accuracy there. Okay. And for the different conditional probabilities, also, you should be able to get reasonably good accuracy. All right. Okay, any questions? Yeah.
I'm just going to ask, like, D is the number of possible values for each node.
No, D is the number of features. So D is the number of nodes. Yeah, so basically you can imagine the number of nodes is huge, right? But the number of possible values for each node is small. So basically think of it like some kind of, your genomic sequence, right? It's ACGT values, but then the number of nodes is very big. Okay, and most of the time you can imagine it as like a Markov chain or something, but there may be some, edges missing or some additional edges, and that's what we're trying to figure out this. Okay, some splits or whatever we have. Okay. All right. So the suggestion was, maybe if you give me a tree, what to put on the conditional probabilities, I would just use the sample estimates. Okay. So, maybe I'm going to use, okay, p hat of x1 given x5 here, p hat of x4 given x5, p hat of x2 given x4, p hat of x3 given x4. Okay, that makes reasonable sense. Okay. Okay, so by counting frequencies. Okay. So where are we now? We said, okay, our goal was to estimate PT star. Okay. And we are saying, given a tree, T, we're going to use PT, which is, let me write it something like this. Okay, it's just, I mean, we're trying to estimate PT star, but given a tree, we are essentially working with this estimator. Right? And I'm going to put hats here, right? I'm just going to say, now given this tree, my candidate estimator right now is PT hat equals the product of these 5 things. 1, 2, 3, 4. Okay. And of course, there's P hat of X phi. Okay, so I would just multiply these 5 things, and then that's our current estimate. So how well does this do? So that's the question that we have to answer. Okay. So if I want to estimate, how close am I to the true answer? How well does this do? So can I say something about is this a good estimator in terms of distance? Am I getting close to the true distribution, or am I still far? What do you think? Yeah.
Done is we the probabilities that maximize the likelihood of the data given. But I mean, so we don't observe a T star, but we know in this example that T is not the same as T star.
Exactly, right? So if a T was good, somehow the right T, then of course right tree, then we might be okay. So in some sense, we can split the error into 2 things. We can think of the error, there are 2 sources of error. Using estimated values, i.e. P hat T versus PT. Right, so I'm using estimates for the conditional probabilities. So that is one source of error. So even if I have the right tree, I'm not going to get the exact conditional probabilities just from the samples, right? Because I just have few samples. But presumably with enough samples, you can drive down the error small enough. Okay. The other source of error is we might be working with the wrong tree. Okay. So let me say that the first source is very easy to control. Okay. So with something like The first, source of error is very easy to control, right? Because you're just estimating relative frequency. If I gave you a coin and I told you, okay, so some biased coin, tell me, what is its bias? If I toss it 1/epsilon² times, I can compute the bias just by averaging within error epsilon. Okay, it's like stat 101. If you ask me what is the chance that x1 equals 0, I can just take 1/epsilon² samples, average it out. It'll give me a value which is very close to it. Okay, which is epsilon close to it. So the first source of error is standard stuff, so we can pretty much ignore it. Okay, so let's say we took care of that for now, and we took care of the first source of error. So even though we are working with frequency estimates, we can pretend as if, so let's pretend we computed the conditional probabilities exactly. Okay, just for how to develop the algorithm further, and then we'll see that all of these errors kind of work nicely together and they won't hurt us. Okay, any questions about this assumption? No, right? Because you're just trying to say, okay, 0, 0, I can estimate it with an error epsilon relatively fast with few samples. Okay, so that part is fine. So what does this mean? So then we have to worry about the second source of error. What if we have the wrong tree? Even if I gave you all the conditional probabilities properly, how do you figure out which tree to use? Okay. So how to find the right tree to use? Okay, somehow we need to handle this quantity, even though we have the right conditional probabilities, but we don't know the right tree. Okay. And here's where some magic of KL divergence comes in. Okay. And let me just say, few things about it. So what is PT star, right? So we have a nice enough formula for it, right? So PT star is basically you take every edge in the tree and you put the conditional probability and multiply them. Okay, that's the formula for a base net with structure T star, right? And what is PT is the same formula, but with a different tree. Okay. So right, so in this example, for instance, we'll have PT star is P of x5 times P of x2 given x5 times P of x3 given x2 times P of x1 given x3 times P of x4 given x5. Okay. And then PT is something like this. So I'm writing it in somewhat painful detail again, just to give a hint about what's going to happen. Okay, so we have these two formulas. Somehow we have these two distributions that we have to compare. Okay, maybe if you're given these two things, you might wonder, so what are we interested in? We are interested in what's the KL divergence between these two distributions. So remember, KL divergence had this weird looking formula, right? So we said this is summation or all things in the sample space of PT, basically PT of A times T star of A times log of PT star of A divided by. Right, this is the formula for the KL divergence, which we can break it up as this is the entropy of T star, and then you get minus the cross entropy. Okay. Now, the nice thing is, remember, we're trying to optimize over all T, right? So T star is some fixed quantity. So when I'm trying to do the KL divergence, this is kind of a fixed number. This doesn't depend on T exactly. The first term is T independent, so it's some kind of shift. So we're trying to find a T which minimizes this KL divergence quantity. So that's the same as saying I want to maximize this cross entropy. Okay. But in fact, what happens is, you can see if I take the log, what is the log of products? It becomes sum, right? So that's the nice thing about KL divergence. When your distribution factors nicely, cross entropy becomes something very nice. Okay. Instead of having like a complicated product, when I take the log, what I'll end up getting is sum on the edges of the tree. Okay. So I can write this as entropy of T star minus summation A, PT star A times, for every edge, you get some expression. I'm not going to do this computation too much, but I just want to show you something that it's not like rabbit out of the hat. Okay, so you get some expression like this. Okay. And if, when I have two summations, one thing I can do is change the order of the summation. Right? And I can change the order of the summations. I can say what you have is for every edge in the tree, I need to compute something like this. Okay. Still looks somewhat bizarre, but I want to say this is not as weird as you would, not as bad as what you might have expected before doing this simplification. Right? You have some summation over the edges, but tree edge, there are only n terms in some sense. A tree has only n minus 1 edges, so you get that thing. And then you have this expression here. Okay. And so one thing that Chow-Liu did was further kind of play around with this. You just had to do some manipulation with logarithms, and then you end up with this very beautiful formula. Okay. So the KL divergence between PT star and PT actually turns out to be the exact form is not very important, but let me write it down anyway. And this will introduce one more sort of really phenomenally important quantity. And okay, what is that? It's going to be Actually, let me just write it. So J star minus summation. Okay. So if you simplify it, you get this beautiful formula where J star is something that only depends on T star. Okay. So it doesn't depend on what T you pick. It's just a property of the distribution. In fact, J star, if you work out carefully, is essentially entropy of T star. Okay. So, sorry, it's minus the entropy of T star. Oh, actually, this is negative entropy because entropy has log of 1 over P. But it's not important. It's this plus summation I okay. So you get this beautiful formula saying the KL divergence has some quantity which depends only on T star minus something over the edges within T. Okay. But what is this I of XU, XV? That's the mutual information between the two variables. Okay. So here, I of XY is mutual information between X and Y. Okay. So what is mutual information? Intuitively, it captures if I have two random variables, right? Mutual information tells me how much information one random variable has about the other. Okay, if they're two completely independent ones, then knowing the first one tells me nothing about the second, right? Whereas, like, if they're identical or like simple functions of one another, knowing one can tell me everything about the other one, right? If I toss a coin here and someone else tosses a coin in a different building, then the mutual information between those two coin tosses will be zero, right? Because I don't know anything about the other coin toss. Okay, and there is a closed form expression for it. A summation or all A comma B of oops, sorry. Okay. So the mutual information has this expression for it, and intuitively it is the KL divergence between the original distribution that you're starting out with, the joint distribution X and Y, and two independent copies of it. Okay. So if okay. So as I said, the exact formula once again is important, but for us, there is a formula which again Shannon figured out what the right formula is. And lo and behold, somehow when you do the calculation for the KL divergence for the distance between PT star and PT, that's exactly what shows up here. Okay. And I mean, this is a formula that you can work with, but intuitively what you should think about is the following, right? So let's say I have a random variable X. Then what is the mutual information between X and 2 times X? I mean, just think in terms of like, is it high or low, or what do you expect? It should be full. It need not be 1, like, but it's basically whatever is possible is going to be there. Okay. On the other hand, let's say X and Y are completely independent. Then what do you expect the mutual information to be? It should actually be 0. It will be 0. Okay.
Sorry, I have a question. Why is the X and 2X case not 1?
Because X itself might have a lot of entropy. It's basically going to be the entropy of X.
Oh, I see.
Right? If X is deterministic, then there's nothing to begin with. So there's nothing that's going to be there, but it's actually going to be just the entropy of X. Okay. And this case, you can kind of see from the formula too, right? If X and Y are independent, then the joint distribution is going to be the same as the product of the two things. So these two will be the same. So log of 1 is 0. So you immediately see 0. Okay. And it has some amazing properties. Like it satisfies this thing called chain rule. And also, most importantly, and again, this is not something we really need, but it's always non-negative. Yeah.
Make sure I understand this. Is there like a bound on the range of I other than it being non-negative? Like, could
it is non-negative. It can be high, and you can always show that it's at most the entropy of X.
If we like saw this number in isolation, not that helpful. We'd also want to know the entropy of X.
Exactly. Yeah. Yeah.
The expression for regional information. Right? I thought the independent part is on the
Let's see.
scale divergence of the joint distribution.
Okay, well, let me confirm. I mean, that's important because it determines the non-negativity, right? Yeah, you are right. It should be in the denominator. Yeah, it should be in the denominator. Okay. Okay.
I guess I was also wondering, like, how does this derive from where the
Right. I mean, we kind of sure got there halfway, like, you got until here, right? And the rest of the calculation is a little bit like hairy manipulation.
Okay.
It's not very hairy, but you had to do like, 5 steps of manipulating the logarithm.
Is it? Oh yeah. Are we also missing logarithms?
Oh yeah. So let's see.
Sorry, I just
Yeah, you're right. There should be log here. Right, because we took the log and the product became sum, but it should still be sum of logs. Okay.
so essentially you can remove the part.
Right. So what happens is, you have summation or A, but then you have only like XV and XU here. So first of all, like, you can get rid of the other variables in this. And then you get XU and XV, and then you have to do like, you use the formula for base net for T star, and then kind of do some further things. Okay, so like, if UV is an edge, then it changes something. If UV is not an edge, something happens, and you can work through that. Okay. Yeah, I mean, I don't have an intuitive explanation why it kind of simplifies to it, but the math is not too complicated, but it is like, 4 or 5 steps. Okay. Yeah, but it's amazing that, somehow they thought of doing this computation and it turns out to be so clean. Now, you wouldn't have expected the KL divergence between these two things to be so nice, right? Like, if I ask you what's the KL divergence between these two distributions, now all I need to do is basically there's something that only depends on T star. And then for each edge, just compute the mutual information and then subtract it out. Okay. All right, so that's where we are, but Okay, so let's take some summary out of this. Okay, the punchline and the most useful thing for us is the following. Given any tree T, the KL divergence between the tree that we can construct by looking at the empirical samples and the other one has an expression like this. Okay, so now, okay, recall our goal, right? Our goal was to find the T which minimizes this. Right, we said, I want to find the tree which kind of minimizes the KL divergence. I don't know what the right tree is. I want to minimize that. So what does that correspond to? This term doesn't depend on T. Yeah. Maximizing this. Right. So intuitively you're saying, okay, I have a bunch of random variables. Pick a tree which maximizes the sum of mutual information on all of the edges. Okay. So our original goal, find T to minimize becomes equal to find T to maximize okay. You might wonder, okay, I'm only given samples, maybe I don't even know what these mutual informations are, but you can estimate it, right? Because you're only looking at distributions with like really 2 coordinates. I can compute all of these probabilities within some error, and I can estimate the mutual information values. Okay. Now, parenthetical remark, we don't know I of XU, XV exactly, but we can estimate it to error epsilon using 1 over epsilon squared sample. Okay, so this part is again relatively straightforward because I can estimate the joint distribution on any 2 coordinates really well with only 1 over epsilon squared. Okay, so even if I told you all of the mutual information values, how do I find the tree which maximizes the sum of the things? Any suggestions? Okay, so let's see what we want to do, right? We have like, let's say we had 5 nodes. Yeah.
I had a question about why this. Because this.
So basically, for things other than trees, you don't get such a decomposition. Right? If it's not a tree, you don't have 2 variables, you might have many, many variables. Okay, so what happens then is you don't get sum over edges, you get sum over like, subsets of things. And that's much messier. Okay, does it make sense? Yeah. It's a good question. Like, we are using the tree property like very strongly because that's what simplified it to only sum over edges and not over some like supersets. Okay. All right. So we don't, we don't know these values exactly, but we know them reasonably accurately. So let's even pretend we have those values. Okay. So what can I do? Maybe just as a crude estimate, I have all of the mutual information values, and I have to pick out the tree which has the maximum sum. maybe I and mutual information, by the way, is symmetric. Like, how much information X tells about Y is the same as what Y tells about X. Did I get all the edges? Yes. Okay. So you have all of these 5 vertices, maybe I'll say, okay, what the mutual information between these two turns out to be maybe 0.1, here it's 0.2, maybe here it's 0.9, maybe here it's 0.5, maybe here it's 0.01, maybe here it's 0.6, maybe here it's 0.7, 0.8. And did I miss anything? Yeah, this one, maybe here it's 0.3. Yes, I compute the mutual information values, I get this. And what do I need to do? I need to pick out these 3 which maximizes the mutual information. How would I do that? Have you seen this question before? Exactly, maximum spanning tree, right? So what would you do? Like, the maximum spanning tree here would be, you should pick out this edge and maybe what else would you do? This edge and this edge and then this edge. Right? So we are really trying to find the maximum weight spanning tree in the graph where the edge weights are right. And we have many algorithms for finding the maximum spanning tree. Just as you could find the minimum spanning tree, finding the maximum is just kind of, you can negate the things and then minimum is maximum. So minimum, maximum, both are the same. You can use Kruskal's algorithm, you can use Prim's algorithm, you can use all of those algorithms. Okay. And you can do it in linear time. If the number of edges is m, you can do it in essentially like O of m log m time. Okay. So this leads us to this beautiful Chow-Liu algorithm and the following. Okay, so now with all of that thinking that we did, the final algorithm is actually pretty simple to describe. So what does it say? It says the first step, use the samples to estimate the mutual information ixij for every I comma j up to some error. Let me say delta. Okay, we're going to use better accuracy for the estimations. Okay. And then what should we do? Form a weighted graph. Where weights are exactly the estimated mutual information values. Okay. And then you say compute T Chow-Liu to be the maximum spanning tree. Maximum spanning tree just means that find the tree which maximizes the sum of weights. Tree means that there are no cycles and everything is connected. That places some constraint, and you have to do it so that you have the maximum weight possible. Okay. let me call it G in G, right? And then you output PT as your approximating distribution. Okay. It's amazing that they did this in 1963. Such a clean algorithm, right? And they said you form this mutual information thing, and then you find the maximum spanning tree. So it's a very kind of combines like information theory with graph algorithms. Okay, for nowadays, at least we know maximum spanning tree is a very commonly solved problem, but back then it would have been like a very sort of novel use of something for something that you wouldn't think it's useful for. Okay. All right. And I should say that given a graph on D vertices, we can find the max spanning tree in time, essentially that is D squared. I mean, it's really a linear in the number of edges, but the number of edges for us is, could potentially be full. So, that's okay. Okay. I think this is not even allowed. All right. Any questions on this? Okay. So the only thing that we need to do is some kind of bookkeeping to figure out, how much error do I need for this so that my final KL divergence is small. Okay. So what do you think? If I estimate each of these mutual information within error delta, what's my final error going to be? Well, I'm adding D such values, right? And every tree has D such values. So, if the actual thing I have like some plus or minus delta here, right? I could have something like this plus or minus delta, then the final error KL divergence between PT star and whatever Chow-Liu algorithm outputs is going to be at most D times delta, right? Because you're adding D terms, and in each term you have an error of delta. So in the worst case, they'll all add up. So you'll get D times delta. Okay. So if I want this final error to be epsilon, then set delta equals epsilon over. Okay. So you have to estimate each of the mutual informations within error epsilon over D. And once you do that, you can put them all, just add them up and you get KL divergence at most epsilon. Okay. Any questions? So in terms of sample complexity and runtime also, this is pretty good. It says pretty good, but we'll see, in some cases it's still not as good, but it's still a good start. If we have O of D squared by epsilon squared sample, then Chow-Liu algorithm gives me a tree T such that Okay, so you'll have runtime which is quadratic, and you need a quadratic number of samples because to estimate the mutual information within error delta, you need roughly 1 over delta squared. Okay. All right. Make sense? Any questions about this? And since then, people have been trying to extend this to, tree structures are kind of nice, but maybe they're a bit too restrictive. What if you don't have trees? There's some kind of extension called junction trees, which generalizes it to a little bit to graphs with small tree width, which is a generalization of trees and so on. But this, I think, is the cleanest setting of Bayesian nets where we can actually learn it pretty well. Okay. So summary, can learn tree structured Bayesian nets in quadratic samples and time. And an active area of research, I mean, even to this day, is find other settings that we can learn properly. So there's still a lot of work that happens around trying to find other settings where you can learn the trees properly, not learn the Bayesian networks. Okay. And there are also questions like sometimes maybe I don't care about learning the entire tree. Maybe I'm interested in some weaker properties, something called maximal posteriori inference problem. So, there are many questions like, even quadratic is sometimes too high, can I do it linear time in some cases and things like that. Okay. And that's all I wanted to say about directed graphical models or Bayesian nets. Okay, and our next topic is going to be undirected graphical models, which are somewhat related to Bayesian networks, but also kind of a pretty different area by themselves. And they come more from physics, I would say, than from statistical modeling. Okay. All right, let's take a 5-minute break, and when we come back, we'll switch to undirected graphical models. Okay, so undirected graphical models are, again, a model for distributions. And once again, they give us a language or calculus to talk about conditional probabilities. But now there is no directionality in how the dependencies go. Okay, so one thing about Bayesian networks is you can think of it as almost like, I mean, definitely a weak form, but some kind of causality, right? It's saying, okay, X1 is the first one, then X2 comes, you generate X2 based on X1 and then something after that and so on, right? So the directions tell you something. In undirected graphical models, you don't have such a thing. And you have a distribution with, again, let's say D features, each over some alphabet. And you're also given a graph let's see, a dependency graph. G for the distribution D. Okay. And so let's say, for example, I have this graph. Okay, so maybe this is my graph. Now, so given this distribution D, we'll say it has the dependency graph to be G if the following holds, in the sense that when we when I tell you this is a dependency graph, it doesn't necessarily mean that like somehow because there's no edge between 1 and 4, those two variables are independent, but it tells you something about conditional independence relations. Okay. In particular, we say D satisfies, it's called pairwise Markov property with respect to G if for every I comma j that have no edge. Okay, so if an edge is missing, then it tells you something. Okay, the edges themselves are not that, they're not telling you much, but the missing edges tell you something. And what do they say? They tell me that xi and xj are independent. So when there's no edge, you want to say they are independent, but not directly. They're independent conditioned on all of the others. Okay, so for instance, here, there's no edge between 1 and 4. So what this does tell me, it tells me that, so this graph is a compact way of representing all of the following conditional independence relations. In x1 and is independent of x4 given x2, x3, x5, right? And what else? I can say x1 is conditionally independent of x3 given x2, x4, x5, and so on. Like, I can say x2 is conditionally independent of x5 given x1, x3, x4, and so on. So for every missing edge, I get this relation. Okay, so whenever these hold, we'll say the distribution satisfies the pairwise Markov property with respect to the graph G. Okay. So the graph encodes lots of dependency, non-dependency relations. So that's the first notion. And then there's another notion which is called local Markov property. So this is local Markov property. So we'll say D satisfies local Markov property with respect to G if same thing as before, but now I don't even have to condition on all of the other variables. Okay, so we'll say I comma j not an edge implies xi is independent of xj just conditioned on one of the neighbors. Okay. I don't have to condition on all of the remaining variables. I just have to condition on one of the neighbors. So essentially it's saying, okay, so 1 and 4, there is no edge between them, meaning they could be dependent, but the dependence is only coming because of the neighbors. All right. So if I go back here, then I will have x1 is independent of x4, condition just x2 and x5. I don't have to condition on x3. Okay, because the neighbors of 1 are 2 and 5. Similarly, I can say x1 is independent of x3 conditioned on x2 and x3. Okay, and I can say x2 is independent of x5 conditioned on the neighbors of 5, which is x1, x4. Okay, any questions about the definition? So you only have to condition on the neighbors of I or j, it doesn't matter. One of the two will be enough to break the dependency structure completely. Okay. All right. And there's a third version of it, which is perhaps maybe even seemingly more powerful. Okay, and this is called global Markov property. So we'll say D satisfies global Markov property with respect to G if, so we said, okay, X and if we started out by saying you have to condition all but I comma J and all but the neighbors now. But in fact, it's okay to not condition on the neighbors, but basically condition on anything which separates the two vertices. Right, so somehow we want to say that the dependencies are really going or propagating through the graph. So if I cut out some vertices which separate the two things, then the dependency will break. Okay. So if xi and xj, I comma j not an edge, implies those two are independent conditioned on any separating set. Okay, meaning any set of vertices such that if I remove them, I and j are no longer connected in the graph. Okay, so meaning subset of vertices such that removing them disconnects I comma j. Okay, so for instance, x1 and okay, so I guess for x1 and x4, you still have to remove 2 condition on x2 and x5. That's unavoidable. But okay, so let's say x1 is independent of x3 condition even on just x2 and x4. Okay, or on x2 and x5. So basically this, oops, if you have something which disconnects the two, that's enough. Okay, makes sense? All right, and it's not hard to see that which of these three things is stronger. What do you think? Well, it turns out that, I mean, if you have global Markov property, then you definitely have local Markov property, right? If I remove the neighbors, obviously I'm disconnecting you from J, because J is not a neighbor. And with some work, you can show that local Markov property also implies pairwise Markov property. Okay. And for most distributions, all three are equivalent. Okay, for most reasonable distributions, I should say. Unless you have some pathological things, all three are equivalent, and it's helpful to think of all three, right? Even if I tell you, okay, you only have pairwise Markov property, then you can imagine you also have the global Markov property, right? So for example, let's say I have once again something like a Markov chain, then a Markov chain will have a dependency graph, which is a path. Okay, so a Markov chain, the dependency graph, a path can be a dependency graph for the Markov chain. Okay, and that we kind of already know, right? X4 is independent of X2 condition on X3, right? So let's say this is Markov chain. So the pairwise Markov property would just mean X2 is independent of X4 condition on X1, X3, and everything else, right? Local Markov property would mean X2 is independent of X4 given the neighbors, which is like, maybe X3 and X5. Right, you have to condition on neighbors of one of the two things. Okay. And global Markov property tells you that X2 is independent of X4 just given X3. Right. And moreover, I can say something like X1 is independent of X5 given X3. Because if I remove 3, 1 and 5 become disconnected. Okay, I don't have to condition on the immediate past. I can condition on some intermediate state. And even then, the past becomes independent of the future. Right? So global Markov property is like basically saying pick out any node. If it disconnects them, then you'll get independence. Okay. Any questions about this example? All right. Now, and oops. Just as before, we'll have like, we really have the main similar learning challenges. So what are they? One is structure learning. Meaning given samples from D, learn its dependency graph, G. Right, give me a dependency graph which kind of explains the distribution D. All right. And parameter learning, which is given samples from D, learn the full distribution. Okay. And then something, both of this I mentioned in the context of Bayesian networks too, but I forgot to mention inference. Inference refers to the scenario where you may assume the dependency graph, or you're learning the dependency graph. Both settings make sense. But let's say you even know the dependency graph, and I give you all values of X except one missing entry. Okay. So can I give guess Xi given some partial assignment? Right, like let's say you have a dependency graph, a collection of genes, like somehow, okay, this gene is conditionally independent of something else and so on, but then you don't have the marker for something. Can I fill it up in some way, exploiting the information that I have about the dependency graph? Okay. That's the inference problem. Okay, so all three are kind of nice questions. And to start with, let's focus just on the structure learning problem. Right, so let's focus on the structure learning problem, which is what we did even for Bayesian networks. I think that's a good starting point always. Once you know the structure, you can do lots of things afterward. Okay, so what's the input? The input, as before, is a collection of samples from the distribution D. And our goal is to output the dependency graph. Okay. And is this a well-posed problem? What do you think? But just ask it like this. I want to say there's like a trivial solution which gives me no information. Yeah. Yeah, exactly. If I have the fully corrected graph, then that's a dependency graph for any distribution, just vacuously, right? Remember, we say it's a dependency graph when it only tells me something when there is no edge between two words, right? If everything is connected, then it's kind of, it's vacuously true, right? So it's ill-posed once again, because complete graph is a dependency graph for all distributions. Okay, because all edges are present, but the conditions only say about missing edges, so it's vacuously true. So how would you make it more meaningful? Yeah.
I guess the small.
Yeah, exactly, right? You should not look for like, the easiest explanation, but maybe you should look for the simplest explanation, right? So is there a notion of, kind of find me the minimal, quote unquote dependency graph? Right? Someone told me that there is a dependency graph, which is a tree. Okay, find me a tree there, right? And trees we already saw, but in the undirected case, actually we can do more. And the more part corresponds to the following. So the assumption that's somehow most useful for the undirected case is that the dependency graph D is sparse. So assume that the dependency graph of distribution D is sparse. There is a dependency graph of the distribution which has few edges, right? If everything is connected to everything, why are you even talking about undirected graphical model? Right? It's not a good model. There are no conditional independence relations. There's no point, right? But if there are lots of missing edges, that's when you're saying the distribution has a lot of structure in it. Okay. So if the dependency graph of the distribution is sparse, let's say each vertex has a bounded degree. Okay. Like, maybe case 2, 3, 5, something small. Like, in the case of the path, the degree was just 2. And what if I tell you the degree is 3 now? But it's a small number. Each vertex has only 3 edges that it's connected to. What can we do then? Okay. So we can reformulate this question into something more meaningful. Okay. And where each vertex has degree less than equal to. So I have a bound on the degree, then you have to find. Okay. So for instance, maybe my dependency graph is something like this. Maybe I have just a few edges that are kind of jumping ahead. Okay, maybe instead of depending only on the previous step, I could depend on the previous two steps. Right? In this case, the degree is 4. And I might have many more edges. Okay. And we want to learn the dependency graph. And in many of these cases, now that the degree is actually small, once I know the dependency graph, everything becomes a much easier problem. In some sense, even if I have a million variables and I tell you the dependency graph degree is 4, and I know the dependency graph, it becomes a 4-dimensional question, more or less. Right? Because all the independence things, once I condition on these 4 values, the 4 neighbors, I become independent of everything else. Okay. So imagine I'm trying to, each node corresponds to the presence or absence of some gene, and there are D is like 100, maybe, let's say 10 million, and K equals 4. Okay, so I have a huge graph, but the degree is small. Right? So if everything is independent, then it's kind of a simple problem. But we're saying, okay, maybe it's not independent, but this variable only depends on 4 things. So if I condition on these 4, I become independent. So maybe I can exploit that for inference and everything else. Okay. And in fact, one of the main domains where these are used in is basically things like gene regulatory networks. People use them for, kind of modeling fMRI data and so on. Especially in the applied sciences field, people believe that even if you have many features, maybe the dependency structures are sparse. Okay. And that's the setting to keep in mind. The degree is very small, 4, 5, 10, but the number of features is humongous, 10 million or something even bigger. Okay. And there are many important special cases of this. The whole problem is unfortunately very hard, if I just state it this way. And what I want to do in the remaining lectures is study 2 important special cases. Okay. One term you might have heard before, the other one might be somewhat new. But okay, so the first case that we are going to study is called Boltzmann machines. Okay. And the other case we will study is Gaussian graphical models. Okay, so Boltzmann machines are kind of discrete distributions, and Gaussian graphical models are essentially undirected graphical models where you have continuous value variables. Okay. And these are special cases, special cases, but still very interesting. The algorithms that we develop this sometimes can extend to general Markov random fields, but let's not. We'll start with the special case. So what's a Boltzmann machine? Boltzmann machine, there are some generalizations, but in the simplest form, you have a distribution on D variables. Okay. And each xi has only 2 values, let's say 1 or -1. It's more convenient to use 1 or -1 instead of 0 or 1. But So each variable is like, is this gene present here? Is this mutation present here or not present? Maybe you'll say present is 1, not present is -1. Okay. And it's not just this, but Boltzmann machines correspond to a specific form of correlation. And the motivation for the exact formula comes from statistical physics. So the formula is the distribution has the following. The probability of a particular assignment is given by the following. So remember, when we're talking about these undirected graphical models, we always have a distribution. Okay, so once again, you have a distribution. And so once you have the graph, there is a distribution that you can define as follows. So you have weights on the edges, W12, W15, and so on. For every weighted graph, you can define a distribution where the density is proportional, is kind of exponential in some of these edges of Wij times Xi times X. Okay. So that's the formula. One way to interpret it is saying, I think the main takeaway from this is something like this. The exact formula is indeed important. But if you have if you have sum of things in the exponent, I can break it up as a product of exponents. Right? E to the a plus b is e to the a times e to the b. Okay. So it's saying is proportional to, for every edge in my graph, I have a term which is the weight of the edge times Xi times X. Okay. If the weight is positive, it's kind of biasing those two variables to be positively correlated. The weight is negative, it's saying, okay, these two should be negatively correlated. Okay, maybe height and weight, they'll be positively correlated, and maybe something else are negatively correlated. Okay. So for example, if I take this graph, same graph as here, and I put weights maybe 1, 1, -1, 2, -2, 1. Okay. Then the expression that I have for the distribution is I'll get 1 times x1, x2 plus 1 times x2, x3 minus x2, x4 plus 2 times x3, x5 plus 1 times x1, x5 minus 2 times x4, x5. Okay. So we have some such formula, and this comes from statistical physics, as I said. And the exact formula is not as important, but it is important, but not the proportionality and so on. We'll use it in one way and then we'll forget about it. But just keep that in mind. So Boltzmann machines have this explicit form. Given a weighted graph, I can define a distribution corresponding to that graph. And you can do some algebra to show that when I define the distribution this way, indeed, the original graph will be the dependency graph. Okay. Those are Boltzmann machines. And what are Gaussian graphical models? These are distributions on real value random variables. Okay. If you have a set of real value random variables, perhaps the most used distribution to model them is a Gaussian distribution. Right? If I give you a bunch of data, maybe you'll try and fit like the standard normal distribution or something like that. Okay. So this is denoted as N0 sigma, right? So the mean is 0. And it's Gaussian distribution with covariance matrix sigma. Okay. So covariance matrix means that sigma ij, the ijth entry tells you how xi and xj are correlated. Right, so this is kind of the standard Gaussian distribution. Okay. Well, if I give you a Gaussian distribution, what is this dependency graph? Not very clear, right? If I take everything, it's not very clear what the dependency graph would be just by looking at the distribution. All right. But there's this beautiful theorem from 1972. Okay, so let me say that. For any distribution, we all, you've probably heard about the covariance matrix. And covariance matrix is just looking at the correlation of the entries. Have you heard of the precision matrix? No? Okay, so precision matrix actually shows up in various sort of applied statistic domains, but it's also kind of a nice matrix to know. It's just the inverse of the covariance matrix. So, you have the covariance matrix, it's a matrix, I can look at its inverse. Okay. Assume it exists. If it doesn't exist, don't just do some perturbation or whatever, assume it exists. Okay. And sort of the miracle of nature, as it turns out, is that this was shown by Dempsey in 1972. I mean, I think many people knew about the folklore, but I think he formulated exactly. For any Gaussian distribution with precision matrix theta, the support of theta gives a dependency graph. Okay, given a covariance matrix, look at its inverse. All right, and now add an edge whenever that corresponding entry is non-zero in the inverse. Inverse is some matrix. Maybe it looks something like, okay, let's say I have a 3 by 3 matrix. Maybe I have 1 here, 0 here, and maybe 0.1, 2 here. Oh, sorry, maybe this is 0, maybe this is 1, this is 0.1, and these are 0. Okay, so add an edge between two things only if, so this is 1, this is 2, this is 3. The corresponding entry is non-zero. Okay, and what we'll see later on is that basically the dependency graph is explicitly encoded in the precision matrix. When you add these edges, look at the support, magically you get the dependency graph. Okay. Support just means that non-zero entries. Okay, so whenever so ij belongs to the graph if theta ij is non-zero. Okay, if the entry in the precision matrix is non-zero, just add an edge. Yeah.
Not invertible.
Yeah. Assume it's invertible.
That common that it's not.
Yeah. I mean, basically, you can assume that I perturb it slightly with identity matrix, and then you'll get invertibility. Okay. And there is a version of it even when it's not invertible. You look at the pseudo inverse, but let's not worry about that. Okay. But at the end of the day, you have two nice families of distributions that people have been studying for many years for various statistical reasons. One kind of motivated by statistical physics, and the other from just plain statistics. Okay. And in both these cases, the dependency graph has a nice form. And what we'll try and do in the next few lectures is basically design algorithms that learn them with tiny sample complexity. By tiny, I mean, imagine k is like 3 or 4. Okay. So what we'll try and do is learn it with basically something like log D samples. Okay, so imagine the dimension could be humongous, like 1 million, 10 million. We're saying we can learn these distributions when the dependency graph is sparse with only logarithmic in the ambient dimension samples. Yeah.
Or why we use the precision instead of the.
Right. So the intuition is like, if you remember the formula for Gaussian distribution, okay, so it has something like x of minus x transpose. There's a sigma inverse there.
Yeah.
Right. So, and the sigma inverse is here. And that's why you look at the precision matrix. Okay. Yeah. And I mean, the main amazing thing is that given that, the reason the dependency graph assumption is so powerful is that your sample complexity drops from linear in the dimension to logarithmic in the dimension. So if I just tell you, okay, here's a Gaussian distribution, go learn it, you'll need linear in the dimension many samples. There's no way around it. But if I tell you, okay, this is a Gaussian distribution whose dependency graph is sparse, then I only need logarithmically many samples. Okay, as long as the dependency graph degree is constant, only this is enough. Okay. So especially in applications in bioinformatics, these savings are very, very useful. Because you might have like 1,000 patients, but then you have 10 million features. There's no way you can fit even a Gaussian distribution. Okay, unless you assume some kind of sparsity. And then the question is, what can you do even assuming the sparsity? Okay. So in the next few lectures, we'll talk about these two special cases. And these are somewhat relatively new algorithms. There is a lot of older stuff, but I don't think it's as good. So we'll talk about some new research papers. So it might be a little bit complicated, but I think the underlying algorithms are simple enough and we can connect them to what we learned already. Okay. All right. So that's all for today. And Monday, remember, there's no class. So it's Memorial Day. And on Wednesday, we'll start talking about Boltzmann machines and then take it from there. Assignment 4 will be out today, maybe around 7 p.m., not exactly 6 p.m., but it's 7 p.m.
Office hour before.
Oh, yeah, that's a good question. Sure. Let me